We're going to do a factorial ANOVA today in Excel. I know that you guys did one way last week. You will be doing um, the factorial this week, which is some people might call it a two-way ANOVA or something of the sort like that. But I just call it a factorial ANOVA. Basically, is just you're going to have more than one factor or more than one variable that you're looking at. So we're looking at gender as one. It's a categorical variable, and our we have major as another grouping variable, statistics, political science, and psychology, and we are predicting our dependent variable, which is salary, okay, starting salary. So we have, this might help, this is going to equate to 6 different groups, okay? So we have 3 groups that are male with these 3 majors, 3 groups, all female, of the same majors. So since we have 6 groups, we are going to do 6 different distributions to check for normality issues. We have our outliers. I don't mind if you just check the same way I did, which is just through this major, because I don't see anything that stands out that probably needs to be checked separately. You can check the group separately, but I would just be simple about it and just check based on the major, so you have the 3 bars here instead of 6. So you also have your distributions that you'll be checking, because we are checking for normality here. I want to pull this up real quick. I'm doing this a little different for your write-up, so I'm gonna this is gonna be the same document you're gonna get that you download as a template. Okay, so most of this is gonna stay the same up here. I don't think you're changing anything up here actually, because I'm going to give you the hypotheses and everything that you're going to test. So I just want you to understand, because this kind of gets confusing. For the null hypothesis now, we have multiple, right? So we have the null hypothesis based on the first variable, the second variable, and then an interaction between them. So an interaction is like, so here we have gender and we have major. So this is saying that, so if I thought there was it's called a main effect. Main effect of gender would be that males, all these, on average, are higher than all the females, right? Or, well, not all the females, but you get what I'm saying. The average here is bigger than the average here. If you're looking at major, you're looking at whether one of these 3 columns, or even if they all are, different than each other. So is there a difference within this somewhere, that statistics is different from political science, or political science is different from psychology, or statistics is different from psychology for the starting salary here? But an interaction would be like this. So you have males in statistics, right? So this group. And an interaction might say that there's a difference between this smaller group, so has to have both of those variables, and some other group, or maybe even each of these other groups, or something like that. So if there's an interaction, then that's what it's saying. It's talking about the smaller group sections being different. Otherwise, it's just the larger main effects, right? If that makes sense. So I'm going to pull up your write-up again. So we have research hypotheses that males will report higher salaries than females. statisticians will report higher salaries than the other groups, and there will be an interaction between gender and major. Males in statistics will report higher salaries than the other groups. So our assumptions here, you don't have to write anything for these. This is just kind of a checklist for you. The dependent variable must be continuous, and we have salary here, so we know it's continuous. The observations should be independent, and they are. This is one person, this is one person, this is a separate person. We have no outliers based on this. We have, and now we're to the normal distribution, and I've already created these distributions. You've been doing that. You will need to do one for each of the 6 groups. You have been doing that, so I want you to focus on, don't worry about these numbers down here right now. This is just, if I gave you this, could you understand kind of what it's saying? Like, you know, this is frequency, so most of the values fall between these numbers, right? So for your variable. Now, I could have made this a lot more explanatory, like the starting salaries for males in statistics, but I just kept it basic here because I'm trying to get this done. You guys can put however explanatory you would like up here, but this is fine as well. So then to get the skew and kurtosis statistics, you need to use the data analysis tab. And I know some of you have mentioned problems with having that. This is a add-in, right? So you'll have to go to that, or you'll have to get an add-in, and hopefully you already have that, but I just want to go ahead and mention that now as well. I know I mentioned it before, but I'm going to go ahead and mention it probably each time just in case. So when we check normality, we look at the skew and kurtosis, and again, our range here is plus or minus 2, and all of these fall within that range for males, and as far as the females, the same thing, all of these fall within that range. I wanted to show you real quick in case this would be a problem for you or kind of confusing, to get descriptive statistics of just females or just males here. This is what I did. So I'm only selecting this group, and I do this because it's just to, you can't include these categorical variables here, so with these as well. So this is just kind of how I wanted to do it, to make sure I've got the means for each individual group. Cancel this. But you will get descriptive statistics that will pop up like this. It will not be these numbers, but it will pop up like that. Okay, so now that we have looked at those, we can say normality looks good, right? We don't have any problems with normality. So we can move on to the next one, which is homogeneity of variance. So variances between the groups should be approximately normal. So just looking at variance, I mean, these are big numbers. These are really big numbers. So it's kind of difficult to just like look at it and say, no, it's probably fine. So we're going to go ahead and do the homogeneity of variance. I did it by gender and by major. That's all I want you to do. Don't worry about trying to do any different, like all 6 groups or anything like that compared. So we're just going to focus on these. But for this one, we have males and females. I've already ran the residuals for these, the absolute residuals, and I started off by taking these numbers and getting their means. So we have the means for males, and the mean for males, and the mean for females. and then you'll have to fill in the residuals, which again is just this particular formula. So you just need the absolute value of the score, which is in this case 78,504.56, minus the mean, which is 68,966.06. And I used dollar signs because when I would drag this down, I didn't want it to drag this column as well. So, because I would drag this down here, and it would constantly be using these different numbers here, but I didn't want it to change numbers here. Okay, so there's that. And same thing for this, except female minus female mean, and then absolute value of that. Again, drag that down so it filled up all of the rows. And then to run this, this is Levine's test for homogeneity of variance. I use this F test to sample for variances, and I selected the residuals columns. I selected the labels as well because I did select the labels when I was selecting it. And then I put the output range here. I kept the alpha at 0.05. And it gave me this. So I can look at this p-value and say, no, they're not statistically, these groups aren't statistically different. So there's no problem there. So now we need to check major. Now, major has 3 groups, but we follow the same procedure for the most part. So the residuals you'll have to fill out, and this will be the absolute value, score minus the mean, and I calculated the means by using the average formula. Okay, so, and once you do, again, fill out the residuals, fill it down, so and all these will be positive. If there's a negative, then you've done something wrong, so you need to go back and redo that. But remember, you do the absolute value of score minus the mean, okay? Once you have your residuals, then you can run the test. So since there's 3 groups here, we will have to do single factor ANOVA. Again, this is a Levine, the same procedure like Levine's test here. So we're just running Levine's test on this. It's grouped by column. We have labels. Our alpha is 0.05, and the output range just asks you where you want it to end up. So I'm gonna, since I already have this, I'm gonna cancel, and then this will pop up, and our F is 0.86, p-value of 0.42, so it's not statistically significant. So after these 2 tests, we can say homogeneity of variance is fine. There's no violation. I would not, I think these, if you tried to do it between groups like this, it would be too small of a sample. And sometimes these tests, if it's too small of a sample, it's not really reliable. So this is just too small. I'm not gonna have you guys do that for different tests. It would be more of like a, if you were going to get a job in this area type of thing, you could work with, because I work with large data sets at work. Sometimes there'll be, you know, 1 million observations or something like that. So this is just not the data that is, you're not going to be able to run certain things with small data sets you're going to be using in this course. But okay, so you have the homogeneity of variance assumption met. So no problems with assumptions, so we move on, right? So now we need to run the factorial ANOVA. So we're going to choose the data analysis. Just use the ANOVA two-factor with replication. And you're going to select all of your data. Okay. Okay, you're going to select all of your data. So it's going to encompass everything. You can even include the labels. For this, there are 13 for my sample that I have here. There are 13 in each group. So yours is going to be a little different, though. I think yours is going to be 20. So you'll have to change this number to 20. But for this one, it's 13. So see, I have, this is row 1. So I'm going to have one less than what's here. So that's 26. So I have 26, and it's half male, half female here. So that's 13. So I'm going to have 13 rows or 13 rows for each sample. And then my alpha is 0.05. And then the output range. So once I click OK, it's going to pop up just like the one way that you guys did last week. It's going to pop up like this, except with the one way you had like one row here, right? But with this you have, then this is going to say, I think it said sample, and this is going to say group or something like that. I changed these. You'll need to change those for it to, sometimes they pop up like that and it doesn't automatically make sense. But that's what you need to change it to. So, and you can know which one's which if you kind of think, okay, first of all, the columns, that's what that is. These are the columns where the dependent variable, and that is the major, right? So you just gotta kind of pay attention, and you can also kind of know by the degrees of freedom. So the number of groups minus 1 is going to be your degree of freedom, and gender has 2 groups, so this one is definitely going to be gender. And then you have major, which is 3 groups minus 1, so your degree of freedom there is going to be 2. Now, with gender and major, it looks like p-value is definitely less than 0.05, and in this case also less than 0.05. Anything that's going to have scientific notation is going to be less than 0.05. Okay, so if you don't understand what scientific notation is, 19 is how many places this decimal point needs to go to the left. Okay, so it's going to be 0.001 is what we're going to have to say. P is less than 0.001 because that's just a ridiculously long number here. But we have these are our F values, and you can kind of tell just by looking at these that these are pretty big, right? Our critical values are 3 point something, and these are huge. So our interaction, though, so the gender by major is not significant. So we don't have any interaction effects, but we do have main effects. So gender is main effect. Major is a main effect. And this is an interaction, which it says there, so it's easy to remember. Now, what becomes a problem, so you have males and females. You can just look at the numbers for males and females and know that if you look males, females, all of the numbers for males are larger than the numbers for females in all of these groups. So you know that the mean for males is larger than the mean for females. So to interpret that main effect, you don't need to do anything extra, right? Because you only have the two groups. So you can just look at the means and know. And if you need to go to the homogeneity of variance and look at the means here, that's also fine. Might be easier for you to understand that, so you can interpret it easily there. As far as major goes, you have a difference, but where's the difference? Like, so you know there's a difference, but is statistics bigger than political science? Is statistics bigger than psychology? Is psychology bigger than statistics? Like, you just don't know what's happening exactly. So we can go and we can look at the means. Which right now we only have the means for males and females. If I wanted to pull up the means for these three, I can just do data analysis, descriptive statistics, and select the entire columns labeled. The output's going to be, and this might be helpful for you to put, so the output's going to be here. Okay. So you can look and see the means. Now, we don't really know what the differences are exactly. Like, is it saying that this and this are different? This and this and this. So and there's, it's possible there are multiple differences. So we have to figure out what we need to know. So that indicates that we need to do a post-hoc test. If we have 3 groups, then we're going to need, and a statistical significance, we do have to do a post-hoc test. Now, in this case, we're doing political science versus stats, political science versus psych, and psych versus stats. That encompasses all three of those groups and the comparisons. This is all the possible comparisons we can get here. Okay, so we will, I'll delete one of these to show you how I did it. So first of all, we have to do what's called a Bonferroni correction to our p-value. So I had to figure out how many tests I needed. So this is a pairwise, like when you're comparing 2 groups. So it's like a t-test. That's what it is. I'm basically doing a t-test between political science and stats, political science and psych and stats. So if I'm doing a t-test, you don't have to do great big tables or anything like that, because we are just worried about the p-value here. So what we're going to do, first I want to tell you the Bonferroni correction. Since we have 3 groups, what we do to correct is we take our alpha that we normally have, 0.05, divided by 3. That's it. Very simple Bonferroni correction. So that's your new p-value, meaning in order to consider it statistically significant, that's what you need. So we are going to run t-tests to do that. So this will give you the p-value of the t-test. So we're looking at political science versus stats. Now, I always select in the order that I write it. So I first want to select political science. and then I can put, so that's array 1, and then stats, array 2. It's going to be two-tailed, so we're just calling it two-tailed here, okay? And then we are homoscedastic because we have equal variances, so we can select 2 there. And then you just put another parenthesis. Okay, so you have the first array, the second array, two-tail, and that it's homoscedastic, which was choice 2. So that's equals t-test is what you're going to use here, okay? And then when you click enter, it's going to pop up your p-value that goes here. And I did this for each of these comparisons. And yes, this is significant. Okay. Now, I've done the post hoc tests. There's a difference. But I need to know also how big are the differences. So we have an effect size to calculate. Now, if you had a one-way ANOVA, you could just use eta squared. This is a little bit more, but it's still pretty simple. Okay, so we have partial eta squared, which the formula for that is you take the sum of squares for the effect and then divide that by the sum of squares effect and the sum of squares within, which is error. Okay, so let me give you an example of how I did this. So here is the formula. I'm just going to leave that in your file. So you have the effect. So sum of squares. This is your ANOVA table. Sum of squares for gender. And then you're going to divide that by the quantity of the sum of squares of gender plus the sum of squares within. Okay, and that's going to pop up this. And here is, here is like your little small, medium, large, tells you how big the effect is. So here we have a large effect, and this is an extremely large effect. So that's how we're going to report it. Unfortunately, I'm not sure. I can do different things in higher level statistical packages, but I didn't want you guys to have to worry about those packages because they're much more difficult to deal with. So we're not going to worry about trying to get very specific differences between, like here, you could do Cohen's D for these if you wanted to just kind of get them an idea. But for the factorial ANOVA here, partial eta squared is what you would normally use. So you would just say that these are large effects or very large effects. I would say large for this one. I would probably say very large for that one. But you also, these are general effect sizes, okay? So in Cohen's D, it's a general effect size. For this, in higher level stats, one thing you have to remember is that you're going to find different effect sizes depending on the study. So, for example, this number may be a large effect size in some studies, but not so much in others, which that's highly confusing, but we're not going to worry about those differences, but I do want you to understand. So, for example, if like this is a salary study between majors, right? Majors and gender. So the difference between major, this is like political science versus stats versus psych. That's saying there's a big difference. But in reality, if you look in like you're gonna expect some differences, right? Uh, so it's not uncommon or anything like that, but there's different jobs. You know, it's just kind of general to say that that's a large effect, because there's going to be different fields that have different um, measures to go by. So we're going to stick with this. This is easy to understand, makes sense. This is first level, kind of basic stats. I don't want you guys to worry about um, overthinking it. So just kind of stick with this. Just know that the level of knowledge you're going to come out with for this basic stats is not going to encompass everything that you would need to know to actually go out and do stats and research. It's going to help you. It's going to support that effort. But if you go into grad school, you're going to have to take more stats courses in order to do stats. Just giving you some information because I know a lot of you want to go into some sort of graduate program. So that's just something I want you to keep in mind. You aren't going to come out knowing everything. So please don't try to know everything. Just try to understand what we're trying to do here. So the major difference between this and what you did last week is that since you're adding another variable, you also have to consider if those variables are combined. Like, it's kind of like a Venn diagram. I don't know if that might make more sense, but you have the all the stuff that's in one variable, all the stuff that's in the other variable, but there's going to be overlap here. So we have to also consider what's in there. Like, that's different than what's separately in the groups. So you can't count that variation twice. You have to count it as like an interaction between those two. So I hope that makes sense. So that's really all you're going to need to do for that portion. I'll give you an example file that you can look at of what will need submitted. But again, we do give redo assignments, which has not been something that other stats courses are going to do, but I want to make sure you guys get opportunities to improve your own scores. Okay. So we run this. If we have differences, we need if we have differences when there's a three groups or more, you're going to need a post hoc test, and you're going to need to correct your p-value, and then also effect size. Since there's an effect, we got to figure out how big that effect is. Now for a one-way ANOVA, you can do eta squared, which is just slightly different. It would just be the sum of squares divided by total, but with partial eta squared is slightly different. So, and I hope that explains kind of the differences. And I hope to this point you're kind of understanding the differences between like ANOVAs and t-tests. These are very similar in how they look at the variation, and it's just a matter of how many groups do you have, how many variables are we looking at. So with your t-tests, you had different different types as well, right? So you have the repeated measures, so like a paired or matched sample type versus the independent samples. So this is a independent samples form here, but you can do a repeated measures one of these as well, very similar and how you finish it with the post hoc tests and all that stuff. But still slightly different. I'm not going to make you guys do every single thing in this course because what I want you to come away with is the knowledge of the types of tests that are out there, the limitations of those tests. So we have these assumptions that need met. Okay, if these assumptions are not checked, if they're not met, then the test could have problems. So the findings that they're reported could be problematic. If you don't know if they checked for these things, that's also problematic. A lot of times they don't even report that they've checked assumptions. So it's hard to know, have they even checked if normality was a problem? So you have to take the findings with caution, right? You have to be careful of over kind of overstating findings in that regard, because if they haven't checked any assumptions, you're not sure if this test works for that, because this is it's called a parametric test that go by assumptions. You have non-parametric tests out there that do not have assumptions that they need to go by, like these. So it would be better if someone were to, if you didn't see it reported but they did not a non-parametric test, then that's gonna, it's gonna be okay, but they might have already checked assumptions for parametric tests, right? So we just don't know. We gotta say, hey, did you even report that? So as you're reading your articles for different classes, for this class, you do have to pay attention to how did they conduct this? What did they do? Did they follow the procedures they're supposed to? Was the data appropriate for this test? Because it's messy in reality. So you're going to get missing values, you're going to get outliers, you're going to get null null findings, and just lots of missing values are problematic, and there's just a whole lot more out there than what we're going to be able to cover in one course. So I've taken, I can't even count how many stats courses I've actually taken. So I just don't want you to feel like you're going to have to know everything, because that's just not possible. Okay, so just follow these procedures. Make sure that you've conducted your post hoc tests if needed. Again, if you don't find any, if you don't have significance, you won't find any, you won't need post hoc tests, and you won't need effect size. So the only reason you need a post hoc test is if there's 3 or more groups, and the only way you need effect size is if an effect was found at all. So I hope that makes sense, and I guess reach out to me on the text if you need to. I am going to try very hard to get some stuff done this week. Hopefully I will feel better, but if you do need to talk to me, please, please, please feel free to text that number, and I will respond as quickly as I can. I've responded to everything that I've gotten. So if you have not received anything back from me, but you've texted that, it means that I haven't gotten a message from you to respond to. So please go ahead and send another message. Again, if you have a message, please send it to me and Katie, so one of us will be able to respond as we can. Both of us aren't feeling well, but we are giving extra time for these, so I hope that kind of makes up for not having as much, or not having these up in time. So anyway, I hope you guys know you're doing great. Thank you for the kind words, the well wishes. I hope to feel better soon. So I will talk to you guys soon.